Hello and welcome you to Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Step on inside and we are going to be looking at some things involving sequences and series, wrapping all that up as an overview, alongside exponential functions where we model growth and decay not only on a graph, but in word problems where we deal with compound interest or continuous compound interest or anything of that sort. So I'm going to jump right into it from there. Let's go ahead and get started and take a look at this review, where we can get the PDF down below in the description section and hopefully timestamps down below when I'm able to get to those. So we have about, I believe it's 10 questions, but they come in parts, and we do start with graphs here. All right, so we are going to graph each of the following functions indicating the horizontal asymptote. We are going to state the domain, range, and end behavior for each function. Sounds good. Now, these f of x equations here, they have several parameters involved. And let me actually write out this right here. This would be an f of x equals a times b to the x minus h power plus k. So besides your variables, your y and your x, you have four different parameters they're going to have. Generally, a serves as a vertical stretch factor, and that'll remain the same thing here. We give it kind of a different purpose. I mean, we're going to use it to graph. We give it kind of a different meaning and take on it, but it is a vertical stretch factor. B is your growth or decay factor. Every time x increases by 1, we get to multiply by another instance of b with our distance from the asymptote. H and k are your general horizontal and vertical translations that we have in these things. And you are actually going to start with k. At least that's what I want to do with these ones. If we pull out this information right here, let's go to part A. Let's say the a value there in this case is -4. Your b is e. And e is a constant irrational value. It's around 2.7. We'll start talking about it's around 2.7. H is -1, given that you are subtracting a negative to give it a plus. And then k is a +7, because that is plus k plus 7. So I am going to start with k, and that is graphing at the line y equals 7. It's a horizontal line. I'm going to make it dotted as well. Oh, it's very thick. It's a horizontal line right here, and it's indicating a line that we do not touch or cross. And everything I do personally will be in relation to this value. I'm drawing this first to indicate that the +7 has kind of now happened for me. It's almost as if I can ignore it. I won't fully, but ignore it knowing that this is my kind of my new x-axis almost, you know. Anyway, so ignoring that right here, just ignore it for a moment. A reference point that we can find really has to do with a. This -4 can kind of exist on our graph somewhere. And again, it has to do with from here. If I could make this e to the x plus 1 irrelevant and have the -4 be all that's involved, that would be fantastic. And how do you do that? Getting your exponent to become 0. Because you know what happens when you turn any non-zero number to the 0 power? It becomes 1. And -4 times 1 would give us -4. What I want to do is find the x value that would give me a 0 here. And it's going to be -1. When x is h, your exponent becomes 0. E to the 0 becomes 1, and that's it. Now, why does -1 matter? Because when x is -1, when I shift 1 to the left, my value will be 4 units down from here. 1, 2, 3, 4. That is a reference point we're going to build. And that's why, you know, I say 4 down because the 7's already added, right? If I'm starting from 7, then going 4 down from there, that's where I get a point. There's a reference point. It's at the h comma, what would it be, a plus k, like that. You're starting from there. Now, everything I do from here, remember this distance is 4. It's not 3 up from here. I don't care about that, personally. It's 4 down from here. Every value I do here is going to have to do with b, or should I say e. Every time x increases by 1, I'm going to multiply another instance of e from my distance, from my asymptote. So whatever this is here, 4 units down, this will be 4 times e units down, 4 times 2.7. And I'm rounding that. It's closer to 2.718, whatever. That's going to be close to 10.8. Let me get an exact thing. I have a calculator right here. 4 times e, 10.87. So you get 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.87, getting really close to 11 there. If you multiply that by e again, I think it's getting a little big. I don't think I can fit that on this graph. 29.55. That would be 29 units down from this asymptote. So this goes from 7 plus 17 is 24. I would need another 5 units or so to reach probably around down there, around where it says 100. I can't quite fit it, you know. So I can't really get any more on that side. Okay, we're multiplying by e going to the right. As we go to the left, we divide by e. What's 4 divided by e? And this is honestly one of the only times I'm going to use a calculator on this thing. 1.47, so about 1.5 from here. There's a nice point. Divide that by e, 1.5 divided by e. And you get 0.54, so about a half, from there as well. So you can see, and divide by e, whatever, it gets closer and closer. It's about a third. You're taking about a third of your previous value there. So it gets closer and closer to the asymptote here as we start to approach it, and the other way it takes off, like so. Okay, so there is the graph right there in a nutshell. I got a few points for you. Now we need to, the horizontal asymptote, by the way, is at y equals 7. That's your horizontal. Your domain and range. Domain is going to be all real numbers. As long as we're not referring to some discontinuous whatever word problem with limited domain, there's no restriction on the values we can substitute for x. There shouldn't be a problem there. The range has a tremendous restriction, though, with regard to the asymptote. We will never be above or at this asymptote. We will always stay underneath it. They're not all negative numbers, but this is a negative exponential function as we're underneath the asymptote and continues down negatively, which we'll talk about for end behavior. But the range is y is less than 7. You're going to hit every y value in the world that's less than 7. You'll never hit 7. You'll never be above it. The end behavior says as x approaches positive infinity, as we increase without bound right there, your y values, your f of x's, will approach negative infinity. As we go forever right, we'll find our points go forever down in that direction. Now, as x approaches negative infinity, you can see there's a convergence here. Your y values do not go toward positive infinity. They go up, 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 but up closer and closer to this asymptote, 7. Not even a positive. Your y values approach the value 7. They don't ever equal it, but that's what they approach as x goes closer and closer to negative infinity. All right, part B. F of x equals 5 times 2/3 to the x power minus 1. So in this problem, there doesn't seem to be an h. It would be a minus 0, if you will. The h value is 0. But the a value is 5. The b is 2/3. Not a fun fraction. We'll deal with it. The h value is indeed 0, and the k is negative 1. So I'm going to start with k again like I did last time. Let's go ahead and jump right into that. I'm going to be 1 unit down from the x-axis right there for my horizontal. This will be a positive exponential growth problem. Excuse me, positive exponential decay problem. 2/3 is less than 1. We'll be taking 2/3 of our previous values as we shrink it over and over. Now I'm going, without saying it out loud, I'm going to tell you exactly what I'm computing. So hopefully you can hear it and make sense of it when we do it. Okay, when x is 0, when x is h, this will be turned into 1. 5 times 1 is 5. So without a horizontal translation, my first reference point will be 5 units up from the horizontal asymptote, which, by the way, is y equals negative 1. Every value, as I increase x by 1, will be 2/3 times the size of the previous distance from the asymptote. This is 5 units. The next value over will be 2/3 that amount. Now, 2/3 of 5. Let me write this one out, and the rest I'm going to say verbally. 2/3 of 5 is 5 times 2/3, which is 10/3. 10/3 is 3 1/3. So I'm going to be 1, 2, 3 1/3 up from there. Now, if you kept going, I'm going to keep going as long as my numbers are substantial and I feel like I could do them. 2/3 of 3 1/3 is 10/3 times 2/3, which is 20/9. 20/9 is 2 2/9. So 2 2/9 is like that. 20/9 times 2/3 is 40/27. That's 1 13/27. About 1.5. So 1.5 right there. And let's do one more. 40/27 times 2/3 is 80/81. It's basically 1. And you know what? I'll keep going from there because basically 1 is basically right there, 80/81. And what's 2? I don't care about 80/81 times 2/3. What's 2/3 of 1? 2/3. And then 4/9, that's just under a half. So you can see as this thing's approaching, you can see what's happening there. And I'm going boom, boom, boom. We can get those values. Let's go the other direction. 5 divided by 2/3. Well, 5 divided by 2/3 is 5 times 3/2, which is 15/2, or 7 1/2. So 5, 6, 7 1/2 right there. 15/2 times 3 halves is 45 fourths, which is 11 and a quarter. So what was this? 7 and a half, 8, 9, 10. Wait, 8, 9, 10, 11 and a quarter. So about right there. Let's see if I can fit one more point. What did I say? 45 fourths times 3 halves is 135 over 8. Oh, that's a lot for me. It's just under 17. And I can fit that. It's 17. Oh, I should know this. I think it's 17 and a half. I don't know if that's perfect. I think it might be, well, not and a half. It's close. It's really close to 17. It's really close to 17. So I think it's that number about right there. I think it's 16. What did I say? I think it's 16 and 7/8. I don't know for sure. I'm kind of doing it off the top of my head, but that looks pretty good. So without a calculator, my apologies there. I should know that one. And anyway, so there's that curve. You get that decay. It's nice. I like the problem. Oh, I'm going to do that again. I like the problem, especially with what you can do with the smoother curve, because you can get a lot more points from it. And if we required it, we could. Maybe we're only trying to get 1 point on either side, 2 points on either side, what have you. But if you can fit them and they're reasonable, I like to do it. All right, so we still need to get some more information for this one. We have to get the domain and range, and we have to get whether it's positive, excuse me, not positive or negative, the end behavior. The end behavior. So let me move out these fractions right here. Let's get to domain is, once again, all real numbers. We're going forever left and right. The range, this is y is greater than -1. We're going above the horizontal asymptote there. Your end behavior is as x approaches positive infinity. This time your y values are converging toward that -1. Y approaches -1. And as x approaches negative infinity, y is shooting up toward positive infinity right there. Going forever left, forever up. And I think that's all we needed for these problems here. Domain, range, and behavior. Yes. Okay, let's keep moving forward here. Number 2. Helene paid back $100 in month 1 of her loan. In each month after that, she paid back $50. Write an explicit formula and recursive formula that shows f of n, the total amount Helene had paid back by month n. So she, oh, I got it. I'm sorry. I thought they meant she paid 100 month 1, 50 in month 2, 25, half the previous one. No. She started with 100 month 1, and after that, she paid back more. So this looks like an arithmetic sequence because you're going to keep adding $50 paid each time for Helene that she's going to be doing here. F of n. Now, this is function notation. I've been using subscript notation for my kiddos, a lot of a sub n's right here, but that's okay. We can use f of n function notation. It's no different. It's actually probably what you're more used to outside of sequences. So let's do an explicit rule and a recursive rule. So the explicit formula that we would, the general one before we do this would be function notation, f of n equals, now if we're using f of n, we're going to say f of 1, the value of the first term, plus the common difference times n minus 1. Or if you saw it like this, it'd be a sub 1 plus d times n minus 1. They're both the same thing. Take the first term, and you add the common difference n minus 1 times, one less time than the term you're looking for. So for us, our f of 1 is 100. Our common difference is 50. So your explicit rule would be, for month n, you pay $100 plus $50, whatever n minus 1 times, whatever month you're talking about, minus 1 times. And if you wanted to simplify it, you could distribute the 50 and all that, but this is a good explicit rule. Are we going to solve anything on these ones? No, you're just coming up with the rule and a recursive formula. So let's do that next. So what you're going to do is just simply, you're going to state that to find the value of some month n, you take the value, the amount that she paid from the month n before. This is how much she's paid in total, I should say. She paid 50, but how much she's paid in total, plus that common difference right there. Oh, common difference is 50. So however much she paid the month before, add another 50, and that goes into her total. Now, you also need to state what the value of the first term is here as well. I know some people state that first. That's totally fine. F of 1 is, sorry, not 50, but 100. So these are the two different ways to write these out. That's function notation. I've used subscript notation with my kiddos the entire time, but you know what? You can use either or. All right, that's it for number 2. Number 3. There's a famous story that goes something like this. After the board game chess was created, the king was so enthralled with the game that he called in the creator of the game and wanted to give him an award, a room filled to the brim with rice. I read a story. I can't find my book. I read a story for my kiddos every year. I gotta look for it. It's called One Grain of Rice, and it's like this story. The creator proposed an alternate reward, which he put forward like this. Each day, the king would give him rice based on the squares of the chessboard. On day 1, he would get 1 grain of rice. On day 2, he would get 2 grains of rice. On day 3, 4 grains of rice. And on day 4, 8 grains of rice. What does that have to do with the squares on the chessboard? This payment pattern would go on for as many days there are squares on the chessboard. Okay, so 64 days in 8x8 chessboard. I was going to say, wait a second. So what we have to recognize in this thing is day 1, day 2, and day 3, those are the positions of the terms in our sequence that we're referring to. Actually, this might be a series. It says write a sequence. So on day 1, 1 grain of rice. On day 2, 2 grains of rice. On day 3, 4 grains of rice. On day 4, 8 grains of rice. And this continues. And what we have to recognize is what kind of sequence this is. Not arithmetic. Clearly geometric, as there is a common ratio. That 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. You are multiplying by 2 each time to get from one value to the next. So to write a sequence to find the number of grains of rice on any particular day, what we want to do is use the geometric sequence explicit formula. And it looks a little something like this in subscript notation. A sub n equals a sub 1 times r to the n minus 1 power. To find the value of any term n, take the value of your first term and multiply by the common ratio n minus 1 times. So our sequence, and they say any particular day, that means that's an explicit rule for any day n. Not just for the next day, right? So our rule is going to be a sub n equals, your a sub 1 is 1 times your common ratio of 2 to the n minus 1 power. Now this is better written as 2 to the n minus 1 power, right? Just making sure you're aware one way or the other. The first term is still 1. It is an implied value. You could keep it or not, but you're just doubling your output from the previous day starting from 1. Use that sequence to find how many grains of rice the creator would get on the last day, the 64th day. Be warned, the number is not small. Oh, I can guarantee you this number is not small. 2 to the 10th, we've done 2 to the 30th before, and that itself is already like 10 million or something like that. So this one, this one is going to be in the take those zeros and go on with it. So this number, I don't even know how we're going to write this ultimately. I'm going to use my calculator and do this. Now, it's not 2 to the 64th, it's 2 to the 63rd, right? Because a sub 64 equals 2 to the 64 minus 1 power. Because you have to remember, we start with 1 grain of rice on the first day. We haven't doubled anything yet. We're going to double this thing 63 times. So 2 to the 63rd. All right, yeah, this number, if there aren't enough significant, where's my exponent thing on this calculator? 63rd. Okay. So here in scientific notation, it's 9.22 times 10 to the 18th power. Now there are other trailing numbers here. I'm going to use my computer calculator and see if I can copy and paste a number because they might actually get as many digits as wanted. Oh yeah. Here we go. I'm going to copy and paste this number in for you guys. Let's see if this works. There we go. Oh, did I add another 8? No. All right. There's the actual value there. It's that many grains of rice. I'll tell you what. No, I don't know how to compare it to things, but that's a lot of grains of rice. I'm sure there's more rice there than could fill the inner parts of the earth. I'm not positive, but that's a lot of grains of rice. All right. From days 1 to 10, I don't know if that's true. That's probably not close to true. I don't know. From days 1 to 10, how many grains of rice would the creator of the game get? So use a summation formula. So the thing to keep in mind in this thing is he got 2 grains of rice on day 2, but that means he now has a total of 3 grains of rice because he got 1 on day 1. And the 2, it's not like they added 1 for day 2. He got 2 in addition to it. And when we're talking about the 64th day, guess what? This is just on the 64th day. The 63rd day was half this amount. And you're adding these up, plus the 1 and the 2 and all that. So 64 days, this is just on the 64th day. Never mind all the addition or everything before. Anyway, we're going to do from days 1 to 10, which is essentially 1 plus 2 plus 4 plus 8, etc. All the way to, I think, 1,000. No, I guess to 512. All the way to 512 for the 10th day. But we're going to use a formula for that for a finite geometric series. So your geometric series formula, every teacher kind of writes it different, but it's some form of this. To find the series for the n days, I guess, for days 1 through 10, you are going to take the value of the first term times 1 minus the common ratio raised to the nth power all over 1 minus the common ratio, like so. I've seen another teacher write it as such, a sub 1 times the whole thing, r to the n over 1 minus r. It's all the same thing. A sub 1 is in the numerator. It's all the same thing. So right here, just establish what each little bit is here. Your n is 10 because you're going from days 1 to 10. That counts 10 days over. Your value of your first term here is 1. Your common ratio is 2. So to find the sum of the first 10 days here, and it's going to be close. I think it's supposed to be close to 1,000. The sum of your first 10 days here, you are going to take 1 times, which does nothing, 1 minus 2 to the 10th power divided by 1 minus 2. A lot of this you could kind of do, well, it depends on if you know 2 to the 10th, because 2 to the 10th is 1,024. So 1 times whatever, that's fine. This is 1 minus 1,024 over negative 1. So negative 1,024 over negative 1,023 over negative 1, which is negative 1,023. I probably should have known that. 1,023 grains of rice. Excuse me, for the first 10 days. All right, let's go ahead and move forward from there. 2 more pages of things. Write a function of the form indicated for each graph below. They kind of show you this e, I suppose, because otherwise we wouldn't know that this is representing e. So a times e to the x minus h plus k power. Again, every teacher does this differently. I work backwards from the way that I just spoke about teaching it. What I do, it depends on the kind of problem, because we could set this up as a system, and you know what, I might do it algebraically because I want to come up with some algebraic versions, so I'll do both. But because we have the graph, we can also use the graph as long as everything is kind of countable, that we can work off this. Because they told us this is e, you can kind of say this is going to be e times larger than the previous amount here. So let's come up with everything in full. This is the line y equals k, or y equals 4. That means your k value is 4. We have a reference point right here at negative 1, 7. The negative 1 is our h shift. The h is negative 1 unit to the left. Now be careful, because if you're one of the people like me who says, flip the sign and do all that, we'll flip the sign in the equation. But the h value is negative 1. We are shifting 1 to the left. That's how we pulled out that information. The a value for me in this case, given this left shift, is going to be 3. This thing is 3 units up from the asymptote right here. We want to go a units up when we have 1 shift to the left, and that's the one that I'm referring to as far as this reference point goes. This 7 is irrelevant to anything except it's 3 plus 4. It's your k plus the 3. But for me, the 3 is really what matters with regard to this shift, because this, if this is 3 up from the asymptote, this is 3 times e up from the asymptote. So your b value being e, we already know that, but this is 3 e times farther from the asymptote than the previous value was as x increases by 1. But this is all the information that we needed to pull out of here. So this is going to help us create the equation f of x equals, a is 3. So 3 times e to the x minus h, that's x plus 1, and then plus 4. That'll be our equation right there. I stated I'd do it algebraically. I'm not as inclined to do it when there are horizontal and vertical shifts. Maybe I'll save it. I know there are ways to do it, but given the graph, the only time I'd ever really like to do it algebraically is if they only come in the form y equals a b to the x power. We can do it in the other things. I might go back at the end for that, just to make sure that I feel like I'm comfortable doing it the way that I would. Because what I would do is I would shift this thing 4 units down. When we do division of our b values, we have to make sure that we're subtracting things that are also translated. There's just a lot involved, and because there's an e there as well, well, we already know that b is e in that problem. We already know that b is e, so maybe it's not too big of a concern. I'm thinking about going back later, but that's how I would do it based on the graph. All right, this next one, part B. F of x equals a times b to the x minus h plus k. This time we kind of really have to figure out what b is, even though here we kind of just stated it. So let's do the same things as before. This has asymptote at y equals 3. So that is a k value here of 3. I have a reference point. I'm going to use the one on the left to talk about how many times taller this point is afterward. But I have a point here that's h once again. That is 1 unit to the left, so translated 1. And the a unit, we go downward 3 this time. So the a is negative 3 as we go down 3 units as we shift 1 to the left. That's a reference point. And the b value asks, what do we have to multiply our previous distance by? Remember, it's not 0. This is negative 3. And they said this is negative 1.5, so this is negative 4.5 right here, because that's 4.5 down from negative 3. So we're going from negative 3 to 4.5. And, you know, we're asking ourselves, what value of b are we multiplying by to get that? And if you're really uncertain, make it an algebra equation. Negative 3 times some b value is negative 4.5. Divide both sides by negative 3, you'll figure it out, right? Divide one value by the one before it. That's what we would do in a common ratio. And that number, I want to be right, that's 1.5, right? B is 1.5 or 3 halves. So a lot of times we see fractions in those things. So I'm going to go ahead and just write that because that is the equivalent. B is 3 halves. So this is going to be f of x equals negative 3 times 3 halves to the x minus h, the x plus 1 power, plus k plus 3 right there. And that should be your equation. So like I said, there may be an algebraic version that I'd like to show to you guys. I want to make sure that I'm confident in speaking on it because I'm so comfortable with the graph version of it. As long as there are no horizontal or vertical translations, I like doing the algebra versions, but with these things involved and the graph shown, I really like the approach that we're doing here that's opposite of how I was graphing them. For now. All right, number 5. Find the sum of each series below. Make sure to substitute into the correct summation formula. So this first one, we're doing 80 plus 40 plus 20, etc., all the way to 5 halves. It's a finite geometric series here, but we have to find out, how many terms there are. And you know what? I'm going to work recursion until we determine what that thing is. We're not working on anything. There's something called logarithms, which you're about to get into after this unit. We're not working on logarithms right now. So let's just kind of talk about what happens after this to get all the way to 5 halves here. So this is the first, second, third term. As you can tell, by the way, I don't know if you can tell, but as it appears, your common ratio is 1/2. We're multiplying by 1/2 each time, dividing this by 2, if you will. So 1, 2, 3, 4, 5, 6. 5 halves is the 6th term in this series here. Now, we could add these up. Ideally, look, our answer is going to be 120, 140, 150, 155, 157.5, 157.5. That's going to end up being the answer, or we can write it as a fraction, whatever. So let's see if we can get that number through a formula means, just to make sure that we're doing things right. We want to know a geometric series thing works as we did before. So once again, your common ratio is 1/2. The value of your first term is 80, and there are 6 terms in this series. So to find the sum of your first 6 terms, this is 80. We take the value of the first term times 1 minus your common ratio raised to the n power over 1 minus said common ratio, like that. So this becomes 80 times 1 minus 1/2 to the 6th power. That's 1 over 64. This is something, I'm going to work this out in a calculator actually. And 1 minus 1/2 is 1/2. So this is fantastic. That's also 0.5. You know what I'm going to do with this to make it easier for myself? Dividing by 1/2 is multiplying by 2. So I'm going to take 80 times 2 and get 160. I'm going to get some parts that are a little helpful for me when it comes to the calculator. So you don't accidentally do something like type divided by 1 divided by 2 and you don't put it in parentheses or something like that. These are little things that can help you along the way. So 160 times 1 minus 1 over 64 will give us 157.5. That was the number we were talking about from before. So that is the series. That is the sum of your series right there. Geometric series, by the way. This one appears to be an arithmetic series. We go from I equals 1 to 12. This is the summation sigma notation right here of 9 plus 5i. Essentially what's happening is you're going to substitute 1 into this thing. 9 plus 5 times 1 plus, and then you would do 9 plus 5 times 2 plus 9 plus 5 times 3, like that, all the way to 9 plus 5 times 12. Whoops. 9 plus, I'm not going to do it like this. I'm just giving you the idea. 9 plus 5 times 12. So 14 plus 19 plus 24 plus, as you can tell, and you know what's kind of nice about this is you're establishing for yourself how 5 represents this common difference. It's an arithmetic sequence. 5 represents the common difference here, and then plus 69 there. So you keep going over and over all the way down to that one for 12 terms, but it's nice to show it's an arithmetic sequence. You have a common difference. You got to find that last term anyway. You have the first term. All that stuff is involved. So it's kind of nice to show what that thing's going to do when all's said and done. So once again, let's figure out what we need. For an arithmetic series, you're going to pair off n terms right here and add up your first and last term. You can add up any such term set as long as they are bookended from first last or second to last, third and third to last. It's best that you just use these because it's most often the easiest ones you know how to find. So here we go. Your value of your first term will be 9 plus 5 times 1, which is 14. Your 12th term, being your last term, will be 9 plus 5 times 12, which was 69. Your number of terms is 12. These are the it looks like you don't need common difference here. I'm sorry. So right here, the sum of those 12 terms will be 12 over 2 times 14 plus 69. So this will be 6 times 83. And if I know my math, it should be 498. Let me do it from the beginning one. I'm just going to turn 6 times, I think 498. 14 plus 69. 498. 498. There you go. Okay. Number 6. As you can, I haven't done this, as you can tell. You purchase a collectible comic book for $25. According to the latest price guide, the comic book should increase 7% each year. Okay. Write a function that would allow you to determine the value of the comic book after n years. So with this thing here, that 7% is going to represent, there's a decimal representation for it, and that would be 0.07. And I'm using R here. We're going to consider this. I don't know if this isn't a compound interest problem. We're not compounding certain kinds of things. We can consider this to be a geometric sequence. Well, let me see this. You purchase it for $25. According to the latest price guides, the comic book should increase 7% each year. Never mind. This is a function, not a sequence, because not only do we have a continuous thing here, I was thinking let's make sure we don't talk about it as compound interest, though. Let's not do that. So I'm not necessarily going to call it, well, I'm going to call this R. Your formula here can be represented a lot of different ways. A times 1 plus or minus R to the, we're saying n years. Normally say to the t power. I'm going to say to the n power for you guys right here. This is what I use here. If it's a growth, we do plus R. If it's a decay, we use minus R. If an increase is plus, decrease is minus. We are increasing 7% each year, so our R is 0.07. You purchase the comic book for $25. This is the initial amount, essentially year 0. So this is your A value right here. And then n years, we are plugging in n right there. Let me use t right now, and then I'll plug in n right after that, because this is kind of how I wrote out the formula for my kiddos there. So this is going to be The value of the comic book will be $25 times 1 plus 0.07 to the n power, or y equals 25 times 1.07 to the n power. So after n years, it'll be this much. After 10 years, how much would the comic book be worth? Now this is where n equals 10, so this is 10 years later. So this will now be y equals 25 times 1.07 to the 10th power. What basically happens is after every year you multiply by another 1.07, it becomes another 7% more valuable than the previous amount that it was. So just to humor you, after 1 year, it's going to be worth $26.75. The next year is not just going to be another 175 more, because you're taking 7% of that number. So it's an exponential increase. So when you do 25 times 1.07 to the 10th power, we're going to be getting $49. And if I round up, so my value is, 49.17878 something. So this is about $49. And if we're going to use cents here, 18 cents if I go ahead and round that thing up. There's an argument to cut off the decimals as well, arguing it didn't reach the 18th cent. If you're going to round, that's fine. 49.17. It could be acceptable. Approximately, how long would it take for the value of the comic book to double in value? Use the graph to the right to approximate your answer. Okay, we'll go and use that graph because the other way we would do it is using logarithms. And like I said, we'll stay off from logarithms. I will give you an exact answer, though. I will tell you what it is in just a moment. To double in value. So what we saw was previously, the initial value is $25. What we're essentially figuring out here is, when does this part become 50, right? When does this become 50? And what is the n value that gets you that, right? That's what you're doing. So when is y 50? When does it cross here? What's that approximately? Oh, I don't know. 12 was this years? 12 years from then. You can see it was at 49.18 after 10 years. About 12, no, not 12. What is that? 14? Because these are going by twos. 12, 14, 16, 18, 20. Is that really just 14 years later? I'm going to try this later. I want to see if I can trust this graph. No, that's 64. I don't know if I can trust this graph here. I want to make sure I said that part correctly, but according to the graph, that would be 14 years. I'm going to pause for a quick sec and try and think that over, make sure I'm not missing something there. All right, I did a quick check, and I'll tell you what. So I didn't make a mistake. The graph does have a mistake. I believe this graph is for if there was a 5% increase, that this is for the model. So I tried to match it on a graphic calculator. I believe that this graph is for this right here, 5% increase. We'll go by the graph as far as this answer goes. I will tell you what the what the exact answer should be for this. If you divide both sides by 25 there, you get 2, naturally, because we're doubling. So 1.07 to what power gets you 2? Well, that's going to be, I'm not going to tell you how to do it just yet. That's your teaser. The problem is I don't use this calculator ever, so I got to figure out what numbers I have here. So it's going to be exactly 10.2. Yeah, that sounds better. So, or approximately, because I'm going to round 10.245 years. It's a little more than 10 years, right? I was thinking if we're already at $49 right now, we're certainly going to get close to 50 really, really fast there. So this would be an answer for our model. For this graph, all we're checking on this graph, if you're working out, if you're not looking at this other stuff, if you're doing this graph, you're trying to see how can you read a graph. Doubling means get to 50. Can you line up the 50 with the graph and get about 14 years later for that? Different graph, that's okay. We're still trying to do some things with that. All right, let's go ahead and move forward. Last page here. Yep, last page. If you invested $50 and that compounded weekly at an interest rate of 5%, here's your compound interest stuff. How much would the investment be worth in 10 years? So we're using now a very similar formula that we were just using prior to, only now we got a capital instead of lowercase y, a capital P instead of lowercase a. We're not going to subtract, we're only going to add. And this R and this T will be divided by n and multiplied by n respectively. What we're going to do basically is take that interest rate, splice it up a certain number of times in the year, and we're going to do it that many times in the year. Compounded interest gets you just a trickle more money than before because you're taking more percentages of larger values incrementally over time. Not much more, but we'll see it. So invested $50 here, that's your principal amount right there. That's your initial value. Compounded weekly, there's 7 days in a week, but there are about 52 weeks in a year. And that's the idea here. That's the N. You're going to be splicing up your interest rate 52 different ways, and you're going to be compounding that 52 times. The interest rate of 5% is R of 0.005. And in 10 years, that is going to be your T value. So the amount, the accrued amount that you're going to have right here is $50 times 1 plus 0.05 over 52 to the 52 times 10 power. Now, I don't know if 0.05 over 52 will get me anything other than just, yep, some run-on number. So I'm not going to let that run-on number do its thing. I'm going to crunch everything in the calculator right now. When it says 52 times 10, I'm just going to put 520. You don't know how many times people are just going to raise it to the 52nd power and let it multiply by 10. Not by intent, but by the calculator's order of operations. So let's see, 50 times 1 plus 0.05 over 52, all raised to the 520th power. And this is going to get me 82, I'm going to round it right now, $82 and about 42 cents. It says 0.416, so I'm going to go ahead and round it up to 42. So that's how much the investment's worth in 10 years. I mean, invest more money, guys. $5,000 now it's going to be about $8,200, right? If you invested $50 and that compounded continuously at an interest rate of 5%, how much would it be worth in 10 years? So let's see how much bang for our buck we could get for this rate here. Now we're going to be using instead APERT, A equals PE to the RT power. And remember, E is that value around 2 point whatever. There's an E button on your calculator we're going to be using. This is still P. This is continuously, let's use E. We're not going to have an N involved. R is 0.00 or 0.05, I should say. And T is still 10 years right there. So let's say A equals P E to the R, T, like that. Now 0.05 times 10 is 0.5, so 50 times E to the 0.5, like that. The square root of E, if you will. So 50 times E to the, I always forget, oh, there's the button for raised to the, E to the 0.5 power right there. 0.436, so 82.44. What was the other one? Was it 82.42? Gosh darn it, I want those extra 2 cents. You are going to give me them right now, and you're going to round it up for me, sir. That's right. Continuously compounded interest can really do damage. It could, all depending on how big your money gets and how long you're doing it for. But the point is weekly is already a lot of compounding within there compared to just annual. All of them are kind of within arm's reach of each other, but continuously does get you most bang for your buck. All right, number 9, write an explicit and recursive formula for each sequence. Now, these sequences are written in a table, but the idea is as follows. That's the first term, second term, third term, and fourth term. You are recognizing, hopefully here, that you have an arithmetic sequence as 26 minus 30 is negative 4, 22 minus 26 is negative 4, etc. So you are looking at an arithmetic sequence with a common difference of negative 4. Now your first term is 30, so when we write the recursive formula, I'm going to write that again. Change the color back. Okay, so our explicit rule for part A is going to be, oh, they're using f of n. Okay, I guess I got to use it. Do I have to capitalize it? F of n equals the value of the first term plus the common difference times n minus 1. The recursive rule would be f of n equals f of n minus 1 minus 4, where f of 1 is 30. I said a sub 1 before, but we're using recursive form. So there's your recursive, we're using function notation. There's your recursive rule. There's your explicit rule. Let's go on to part B. Part B shows what appears to be a geometric sequence right here as we go from 60 to 20 to 23rds to 29ths. What is this if not dividing by 3? That doesn't mean your common ratio is 3. You're multiplying by 1/3. And if you're uncertain how to do that, take one term by the term before it. If 60 times r is 20, divide both sides by 60, you get r is 20 over 60, or 1/3. So your common ratio is 1/3. Your value of your first term is 60. So, first term. So, let's go ahead and write the recursive from here. Your first term is 60, and the value of any term n is going to be the value of the term before it, times your common ratio of 1/3. You could put divided by 3, arguably. I wouldn't, especially because in the explicit rule, we just don't. We don't write them as division most often. The explicit rule would be to find the value of any term n. You take the first term, 60, and you multiply by 1/3 n minus 1 times. Now, you must wrap the 1/3 around parentheses here for sake of order of operations. Both the 1 and the 3 should be raised to that power. Otherwise, if you don't do that, only the 1 might get raised to that power, and you don't want that. All right, part C. Part C, we have a common difference of 4 being added each time here. So this is an arithmetic sequence. Your value of your first term is 3. So I'm going to go ahead and write the recursive rule right now. Value of the first term is 3, and the value of the next term is the value of the term before it, plus your common difference of 4. There's your recursive rule. And your explicit rule will be find the value of the term n. You take the value of the first term, 3, and you add your common difference, n minus 1 times. I decided I'm not going to go back and do those graphs algebraically. Sorry. All right, number 10. Determine whether each infinite series converges or diverges. If it converges, find the sum. Okay, so right here, the infinite geometric series formula takes on, it takes on the finite geometric series formula in such a case when r is less than 1, when the absolute value of r is less than 1, when it's a fraction between -1 and +1. And it's infinite. So what you do is you take the value of the first term, you divide it by 1 minus your common ratio, like this. This only applies if your r is between -1 and +1. If it's greater than or equal to, I should write this. If absolute value of r is less than 1, then you use this formula. If the absolute value of r is greater than or equal to 1, your series diverges. There is no sum. You will not use a formula because it doesn't approach anything. See, this is a derivation of this, right? I should put s sub infinity. This is a derivation of this right here, right? And what happens is if you have a common ratio less than 1, 1/2 to the infinity power is essentially 0. 1 minus 0 times a sub 1 is just a sub 1. So all that stuff just kind of goes away ultimately where you have that. All right, so your first one right here, your common ratio is you're dividing by 3. So 1/3, just like we talked about before. R is 1/3. This series will converge. As the series converges, we can go ahead and also find its sum. Generally, sorry about that. I don't know where all these pieces went. I was going to turn it a different color. Generally, I believe, isn't it that when you take a third, I'm not going to misspeak. I don't want to get it wrong. So this is going to be s sub infinity here is a sub 1, 81 divided by 1 minus 1/3, or 81 divided by 2/3, or 243 divided by 2. Let me try and do this in my head. 243 over 2, or 121.5, I think. Let's go and check that. 81 divided by 1 minus 1/3. 121.5. So that's what it converges toward. All right, last two. Now this one has some weird fraction things going on. 128 over 3,125. Boom, boom, boom. Now you have an alternating sign set. So that's going to be a negative common ratio. We have to figure out if this is greater than or less than 1 as we're working on it as well. Let's kind of talk about what we spoke on before, but I'm going to use the smaller numbers that I do have available to me. There are the ways you can kind of talk about what's going on from one value to the next, but let's actually come up with that actual common ratio. Remember, you're working from, I'm going to work the smaller two numbers here. Let's do these ones. 32 over 125. If you take 32 over 125 and multiply it by some common ratio, you're getting negative 16 over 25. Now, what is that number? If you multiply both sides by this reciprocal, right here, 125 over 32, and you work on reducing this fraction, this might seem overbearing to you, but 16 over 32 is 1/2. 125 over 25 is 5. So this is negative 5 halves. That's where your R value is, negative 5 halves, like that, negative 2.5. So that's all that you're getting out of that. Now, this number is outside of the negative 1 to 1 range right here. So this is greater than it. So your series will diverge. There is no sum because the series diverges. Basically what happens is your numbers are actually getting bigger. I don't know if you can tell. That sounds weird to say because both of these numbers are bigger than these ones. But 128 over 3,125, I'm not saying it's close to a 30th, but you know what I mean? It's really small. 16 over 25, that's more than a half already. Your fraction is going to end up going more than 1 later. It's going to oscillate sign, but it's going to be bigger, and it's going to swing back and forth larger. This will diverge. There is no sum on this for that very reason, that the value is more than 1. And lastly, an infinite series right here with, whoa, a lot of stuff. We just got to figure out within here, is your R value between negative 1 and 1? Yes, because it's 1/4. So this converges. And what you need is the R value, which we have, and the a sub 1. And if you could plug 1 into here, but if you also can recognize this as a geometric series, a sub 1 times r to the n minus 1 power, negative 7/6 is your a sub 1. So let's go ahead and substitute those into there. The s sub infinity here is negative 7/6. And I don't like writing a fraction over a fraction. I'll show you what I'm going to do. Over 1 minus 1/4. Okay, the 6 is dividing. The 6 can go in the denominator with all your other stuff. So it can instead look like this. Negative 7 over 6 times. And guess what? This is a fraction inside the denominator. 6 times 1 minus 1/4 is 3/4. Oh, I'm going to work this by hand. I'm not going to let this thing slip and just do it that way by calculator. Unless I kind of have to later. So 6/4 reduces to 3/2. So this becomes negative 7 over, I'm going to double check it, make sure I didn't mess up, over 9/2. Now, once again, dividing in the denominator is multiplying in the numerator. So I'm going to take that 2 and multiply by negative 7. We get negative 14/9. That's an exact answer. See, I don't want to use the calculator and have it give me, oh, I can't do that stuff right with it's the 0.1s. Let's see if I got that number right. Let's first check 14 over 9. 1.5 repeating. So let's see what this one would have given me if I started from that. Negative 7/6, negative 1.5 repeating. So 7/6 divided by 1 minus 1/4 is 1.5 repeating. Yeah. So yes. So negative 1.5 repeating. So negative 14/9 is your final answer there, and I'm gonna leave it like that. Okay, guys, so that ought to do it for this one, and that is your general overview for these problems. Hopefully you got a good gist of what was going on there. This is Mr. Robinson. I want to thank you so much for watching. Enjoy the Winter Olympics behind me. Is that Shaun White? I don't know who that is. Anyway, thank you so much for watching. Take care. See you in the next one.